One thing I have not emphasized in class enough, at least, I did mention it a few times, is the idea of the average value of a function. Average value of a continuous function. This is defined in chapter 5. It's over some interval, say the interval from A to B. This is in chapter 5. By definition, this is a definition. It's 1 over the length of the interval, which is B minus A, times the integral of the function from A to B. That's the definition of the average value of the function. Theorems are mathematical statements of fact that require proof. Theorems are things that are not obviously true, things that need proof. Well, even some easy things still sometimes need proof, but definitions are the way they are because we say so. Nothing to prove. This is what average value is. However, definitions should still make sense. Let's think about an example. Let's say f of x equals x squared, and the interval from A to B, let's keep it simple, is the interval from 0 to 2. What's the average value? I'll abbreviate average as AVE of this function over that interval. It's 1 over 2 minus 0, B minus A, times the integral of f from 0 to 2. So that's 1/2 times the integral of x squared is 1/3 x cubed. Need to evaluate from 0 to 2. I can go ahead and multiply the 1/2 and the 1/3 to get 1/6. So I get 1/6 times 2 cubed minus 1/6 times 0 cubed. And that will be 8/6 minus 0, which is 4/3. 1.3 repeating. So that is what the average value of this function is. So calculating it is pretty easy. But what does it mean? Why is it important? And does it make sense? Here's a little intuition about what it means. Here's the graph of x squared, say. Let's say this is 2, and this is 4 up here. The graph of f of x equals x squared. When x is 1, the value is 1. The scales are not the same here. I'm saying the average value of this function is 4/3. Now, if this had been a linear function instead of a quadratic, if it had been a straight line connecting these 2 points, we've talked about average value for linear functions before. It's halfway between the extremes. The extremes being an output of 0 and an output of 4, second coordinates of those 2 red points. If it were a straight line, a linear function, average of 0 and 4, the extreme values, the minimum value and maximum value is 2. 4 plus 0 over 2 is 2. Halfway between them, there's 2. But our function is not a straight line. It's a curve, parabola, piece of a parabola. I hope it makes intuitive sense that the average value of such a curve that's concave up like this should be lower than 2, because the function, the graph here, sort of spends most of its quote unquote time in lower values than it does in higher values. But why is the answer 4/3? The answer for the average value is 4/3, which is right about here. The average value is defined in such a way that the area under the curve, this green shaded area, is the same as an area of a rectangle of the same base from 0 to 2, whose height is the average value. This rectangle shaded in purple has the same area under the curve. Its area is base times height, 2 times 4/3, 8/3. Hey, that's the same as the integral. The plane integral right there has a value of 8/3. The average value is 8/6 or 4/3 because I had to also divide by 2. This argument works in the abstract as well. Let me give the average value a symbol. I'll go back up here. I'm going to call it F bar. And I'm not going to put an of X. This is not a number. It's not a function. It's a number. If you've taken stats before, you might remember X bar, and X with a bar over it is the symbol for an average, a mean of data. So this notation is supposed to be reminiscent of that. And F with a bar is an average of a function called F. F bar, the average value of F, which is a number, not a function, is 1 divided by the length of the interval times the integral of F over the interval. I can rewrite this equation by multiplying both sides by b minus a. I can say the integral of F is the average value F bar, that's a number, not a function, times b minus a. Right? Just multiply both sides by b minus a. It'll cancel on that side. But the integral is the area under the curve. This integral right there, for this example, is the green shaded area under the curve. And this product is base times height of the rectangle. They have the same area. They're defined to have the same area. And if your little f function represents speed, then F bar is the average speed. The fact that little f is increasing, if it's the speed, means you're accelerating, you're going faster and faster. F bar is the average speed. If you were going at a constant speed of 4/3 meters per second, say, your distance traveled is going to be the same as the distance traveled if this is your speed. Again, these things are things you can feel like you kind of get when I'm talking about it, or maybe you don't get it because you're either having trouble or you're not paying attention well enough. But then like 30 seconds later, you like forget it. So you can't just sit in class and hope to get these things. You have to do things outside of class. That's why we assign homework, both reading and problem solving, so that you spend time thinking about it and problem solve and think about the problems as well, and whether they make sense or not. Interpret them. You should be able to compute average values. Okay, it's not difficult. It's not difficult to compute. And you should know this geometric interpretation. The area under the curve is the average value times the length of the interval, which means the area under the curve is the same as the area of the rectangle, whose height is the average value. And don't let the fact that I'm calling the average value F bar bother you. It's just a symbol. It represents a number, not a function. Or you could think of it as a constant function if you wanted to, but probably better to think of it as a number. It very well could be on there, yeah. And you'll find practice problems at the end of chapter 5. I believe I assigned at least 1 or 2 of those that are related to average value.